the next speaker. I'm honored to invite Professor Stefano Rivella, who is a Ohene Frempong Endo Chair in Pediatrics Hematology at the Children's Hospital of Philadelphia. Dr. Rivella contributed to the development of first lentiviral vector and is currently supporting a clinical trial aimed at curing hemoglobinopathies. He is now developing tools for RNA delivery to treat hematological and metabolic disorder, as well as to target hematopoietic stem cells as a non-toxic approach for myeloablation. And he's the first person that walked me 1,000 steps in Malaysia. Thank you.
Thank you, Ali. It's a great honor to be here today. Thank you for the kind introduction. And I'm really, really happy to be here in Canada, like a fresh break from what's happening in the United States. So today I'm going to talk about a number of things, focusing on alpha thalassemia and X-linked sideroblastic anemia, but I'll try to touch also on some of the other things we're doing, especially the social component of doing a clinical trial, and just introduce some notion that I hope we can discuss later. So these are my, maybe, it's not moving forward. Oh, here. So these are my disclosure, nothing related to this presentation, but I just want to mention that I'm the SAB of this medicine. So if someone wants to talk with me about the differences between phlebotomy and blocking iron absorption, especially in polycythemia vera and additional application, I'm happy to talk about it, as we published the first paper showing this potential mechanism. But today I'm going to talk about the relationship between red cell disorders and gene therapy. Some of the Dr. Lee introduced very, very well, and so I'm going to simplify my life about these novel therapies that really came out to target thalassemia and sickle cell disease. So, as Ali mentioned briefly, I was lucky to be in a laboratory when I was a postdoc where we make the first lentiviral vector for the treatment of beta thalassemia. So I'm very familiar with the bluebird vector and etc. And I know that that vector can be improved upon, and we can make a better product for the treatment of the patient. So a few years ago, when I moved to CHOP from New York City, I decided to make a better vector. And the question was, can we make a vector that is intrinsically safer, more effective, and actually more affordable for beta thalassemia and sickle cell disease? And can we also, then I'll show you, can we use this kind of template to make a vector to cure alpha thalassemia, and then eventually X-linked sideroblastic anemia? So I'm going to talk very briefly about the first part, just to introduce everything else that you will see after the beta thalassemia, because it really the bricks to discuss and present my work on alpha thalassemia really stem from the work done on the first form of hemoglobinopathies. So several years ago, I've been involved in making a vector called TNS9, Memorial Sloan Kettering. It was actually the first clinical trial, failed because basically there was no myeloablation, so there were not really cells I wasn't part of that trial, was already away at that time, but the vector worked pretty well, but basically with no myeloablation, minimal myeloablation, there was no engraftment. And so, but I knew about the vector because I made it myself. I know about the BB305, which is the Beta-Globin vector from Bluebird, and also another vector was made in Italy by the TIGET Institute and Globe. And so I made this vector myself again. I just want to be sure, I had some template to compare. And then we make newer vectors in which we modify both the beta-globin gene and the element that control the expression of the beta-globin gene. So when you make a lentiviral vector, I like to make an analogy that you need two components, apart from the component that bring the vector inside the cells, which is basically HIV, the LTRs, etc., which are really minimal elements of the vector. You need two components that I like to call the hardware and the software. The hardware is the gene, and the software is really what allows the gene to be expressed. And so you want to really modify, if the gene is there in all these vectors, what you can modify to make it better is to improve the software. So basically, once the vector is integrated in the genome of the patient, you want the maximum expression to really be curative. So we compare all these vectors, and at the end of the story, we identify a vector called LS20, that in comparative analysis, both in vitro, patient cells, and mouse model, you can see on the bottom part here, basically was able to make between 40% and 150% more beta-globin than the vector that I mentioned previously. And so with this vector now, at the same time, we established a center, the scientific director of this center called QRED, the Comprehensive Center for the Cure of Sickle Cell Disease and Other Red Cell Disorder, but you will see additional disorder were being included. Jan Kwiatkowski is the clinical director. And this center really has the goal of this center is really to, first of all, to help the patient to see, the same day, all the physicians that can help them to discuss their disease, like, cardiologists, hematologists, et cetera. But also, if the patients are interested, introduce them to clinical trials, not necessarily our clinical trial, whatever clinical trials we believe can be beneficial to the patient. And so then we can provide them some, not only introduce them to the trial, but also psychological support for the families and talking with the specialists for fertility preservation, et cetera. And so this center has been involved in all the trials that have been done for sickle cell and beta thalassemia that have been discussed previously. And now we have our product that's been approved by the FDA, and we're treating the first patient as we speak. So, but the second question is, then can we use this technology and this platform now to work on alpha thalassemia? And so alpha thalassemia is, so it's not as frequent as beta thalassemia, sickle cell anemia, but if you move in Southeast Asia, the hemoglobinopathies is actually alpha thalassemia. So of course, alpha thalassemia is much more heterogeneous, and even if thalassemia and sickle cell, beta thalassemia and sickle cell are heterogeneous. We talk about the many differences and the correlation between the expression of fetal hemoglobin and number of alpha globin genes that modify the phenotype of this patient. Alpha thalassemia is even more complicated because normally we carry 4 copies of the alpha globin gene, and so before really having a phenotype which is pathological, we need to get to a low level of expression of alpha globin gene, can be manifested as HBH disease, where basically you have an excess of beta globin chains, the opposite of beta thalassemia, or you have basically Barrett's hydrophitalis, where basically the kids die in utero unless they are transfused and rescued by this treatment. However, they became immediately transfusion dependent, and so basically they're similar in a way to what happened to the patient affected by beta thalassemia. However, because probably we have less patients in those countries, North America, et cetera, alpha thalassemia has been a little bit neglected. Another problem is also to make a mouse model. Alpha thalassemia has been very challenging. And so there are a couple of models, but basically don't show any severe phenotype. And so one of the things that we decided to do is, first of all, can we generate a new mouse model of severe alpha thalassemia? And then can we apply the similar technology as we did for beta thalassemia, sickle cell anemia to treat these little patients? So I want to introduce briefly a technology we introduced in my lab. I'll come back to this at the end of my talk, even if this is not really the main topic of the conversation today. But basically, a couple of years ago, we developed another technology based on lipid nanoparticles. So these are lipid nanoparticles, basically the same technology we use to inject the COVID vaccine. I'm very, very lucky that I work close to Drew Weissman, who won the Nobel Prize for the COVID vaccine. And a few years ago, I talking with him, I say, can we try to use this technology instead of for vaccine? Can we try to use this technology to deliver RNA to hematopoietic stem cells? And so you can imagine now, if you can do that, now you can basically deliver in vivo information to the hematopoietic stem cells, and this will be a game changer for gene therapy. So as a proof of principle, we showed this is possible. We basically develop a system where we deliver lipid nanoparticles that basically carry an mRNA that express a CRE recombinase. And this CRE recombinase can basically target a portion of the gene in the mice. These are transgenic animals. And if everything works well, then the hematopoietic stem cells became red fluorescent. And so we show basically now we can basically target 100% of hematopoietic stem cells and introduce this genetic modification. So, but why I'm introducing this? Because Alpha thalassemia, as I mentioned before, if you have a very severe model alpha thalassemia, basically dies in utero. So how can we compensate, what's the escamotage we can take to basically create an adult mouse model that has a severe phenotype similar to those patients that rescue in utero? So we made a mouse model where basically it carries only 2 alpha globin genes, the alpha 1 and the alpha 1, while the alpha 2 were already knocked out, eliminated. And then what we did, basically we used these lipid nanoparticles delivering this mRNA, and this alpha globin gene is basically modified with 2 regions called LOXP sites. And when the critical kinase targets this sequence, basically creates a deletion. And so what does it mean? You can eliminate this alpha globin gene when the mice are already alive and adults. And so you can use the phenotype alpha thalassemia without avoiding the problem of trying to rescue these animals when they are in utero. And so we did experiments, and so this works in this way. It's complicated, but basically you can take these animals, you can inject them, you can take the stem cells, you can expose this technology, induce the deletion, and then you can do different things. You can also use these bone marrow cells for transplantation. And this is helpful because I will see that later that I will use this system basically to introduce the corrective gene at the same time. But at this stage, basically, you just want to introduce the deletion. So we want to see what happens if the stem cells don't have any alpha globin gene. And so to our surprise, the first experiment, the student came to me and say, actually the mice after introduction of this mutation have this deletion, they have normal hemoglobins. And I say, well, maybe something happened, the system didn't work well, etc. Let's redo it again. And then the second time came back to me again and say, yeah, they do well. Actually, they have more hemoglobin than normal mice. I say, okay, this is really strange. And you can see here that the blue bars are actually the hematocrit, the number of red cells. So these animals, they supposedly don't have the alpha globin gene. And I say, okay, let's look at more carefully at these animals. And you can see here, these animals have really terrible red cells in circulation, so definitely something is happening. In addition, they express almost exclusively hemoglobin H. So these animals, when the student analyzed them the first time, then the mice were disposed, we didn't look at them for a long time. The second time, we observed these things, and eventually the mice die. The mice die for a number of reasons, but definitely they were not surviving with expressing all hemoglobin H. However, there are more red cells in circulation than a normal mouse, and then I'll discuss this in a second. Sorry. So one thing that we need to keep in mind, these mice make hemoglobin H. Hemoglobin H is a kind of hemoglobin that really binds oxygen at very high affinity. And so this is probably familiar to you that work with patients with alpha thalassemia. And I know I learned a lot from Ali. I'll talk about one of his papers in one of my next slides. We had a really wonderful discussion because when I saw this data, I started digging more in the world of, we don't have patients with this severe form of thalassemia CHOP, so I didn't know how to interpret this data initially. But one thing that really triggered my curiosity is that hemoglobin H, it really has high affinity for oxygen, to the point that it never releases oxygen. So basically you have these all red cells in circulation, a lot, but they basically suck up oxygen and don't deliver, right? So this is number one. I would say the first clue to understand the phenotype of these animals. So the additional important points is that, as again, these are 2 mice affected by alpha thalassemia. You can see a lot of these red cells, very abnormal in circulation, very different from a normal mouse. They don't live longer than normal cells, so it's not because they have a higher survival capacity. They actually survive, the lifespan of these red cells is reduced. And when you look at, this is a urea gel, but long story short, these basically animals have also precipitation of this hemoglobin H on the red cell membranes, which is another feature of abnormal hemoglobin presence in these red cells. So basically, they really have all these characteristics that can expect in a severe model alpha thalassemia. So then we did an experiment to understand a little bit more the pathophysiology in these animals. And what we did, basically, we mixed cells that were wild type in a different proportion with cells that were knocked out. You can see here with degenerated animals that basically had 100% of the wild type cells, or animals 100% with only knockout cells, and then a different proportion in the middle. And so the first thing that you observe after this, and we look at number of parameters, including erythropoietin, et cetera, and so one thing that we first look at was VEGF. Why VEGF? Because VEGF is actually a factor that's upregulated in condition of hypoxia. And so I mentioned before the hemoglobin H binds oxygen at very high affinity. And so in order to demonstrate indirectly that hypoxia was a really important element, and we did other experiments just to show you this data, you can see here that the mice have 100% on knockout cells show high level of VEGF, and this level can go down as we increase the proportion of wild-type cells. Again, indicating that you have 100% of knockout cells, the mice are extremely hypoxic. Now, the data was really striking is about erythropoietin levels. So you can see here, this is basically the mice that were generated with 100% of knockout cells. And you can see the level of erythropoietin. This is serum erythropoietin, okay, in circulation. You can see the level of erythropoietin compared to normal mice. I mean, it's a scale that's like out of proportion. I personally never saw any mouse model that shows so much erythropoietin in circulation. So that basically indicates that there is a really strong drive to make erythroid cells in this animal. Despite the fact they have such a huge defect in making bad red cells, they still have so much erythropoietin that really the system pushes them. And as a matter of fact, they have a large spleen that's full of erythroid progenitor cells. And so I mentioned before Ali, because then I was talking with him, and then because I found out about these studies, and basically say, looking at this patient that are very severe alpha thalassemia, you call them alpha thalassemia major, and I use this term now, basically, and these are patients that are being rescued by in utero blood transfusion, have a very hard time to basically suppress their endogenous erythropoiesis. I need to basically hypertransfuse them. And despite that, the reticulocytes are still very elevated. And so then this, for me, was important because I say, well, I didn't make a mouse model that's completely different from the reality of the clinic. It looks like there is a really strong relationship. You can suppress erythropoiesis, but depending on the quality of the red cells, this can be different, right? And so I like to make this model where basically I show the differences between what happened in alpha thalassemia, severe alpha thalassemia, and beta thalassemia. So basically, we have here a situation where in alpha thalassemia, you make a lot of red cells that make hemoglobin H, and basically this hemoglobin H creates a lot of hypoxia, increases EPO, and that basically feeds back to make even more red cells. So now, if you compare this to beta thalassemia, you have a similar situation, but it's not as dramatic because the abnormal hemoglobin you make, hemichromes, in beta thalassemia doesn't really bind oxygen. And so there is really a qualitative difference between beta thalassemia and alpha thalassemia related to the characteristic of the two different abnormal hemoglobins. And I think this would explain why, if you use blood transfusion in beta thalassemia, you largely suppress the endogenous erythropoiesis, and basically what you see in circulation mostly are red cell donors. But if you do the same in alpha thalassemia, depending on the level of, if you provide the same level of blood, basically you may still see red cells in circulation. And this is an important factor because those red cells, despite they are there, they give you a hemoglobin level, it's a proportion of cells that basically is detrimental to the patient because they don't deliver oxygen, right? Okay, so then we make a lentiviral vector that expresses the alpha globin gene, how this is associated to the work we've been doing beta thalassemia. If you remember, I mentioned before beta-globin, in a lentiviral vector, we use two major elements, so the hardware and the software. And so in alpha thalassemia, obviously, we need to change the hardware, we need to change the gene, right? Because that's what is missing in this patient. But we thought maybe we can use the same software because the expression of the beta-globin gene and the alpha-globin gene happens at the same time during erythroid differentiation. And so actually, this may be even more advantageous because we don't really reach the level of beta-globin that we would like in beta thalassemia. One copy is not equivalent, one copy of the beta-globin gene, roughly 50%. But since these actually in alpha thalassemia, you have 4 genes, we may be able with one vector to actually cover the expression of one alpha globin gene that we expect to be curative. So we made the same strategy. We we first make this hematopoietic stem cells knock out for the alpha globin gene, use discrete technology. At the same time, half of the cells were treated with a vector, and then we see what happened to the mice. And so the bottom line, all the mice expressed the vector, basically were rescued from the disease. So this is a HPLC electropherogram, and basically you can see here that this line here, it's basically this new chimeric hemoglobin. So the chimeric hemoglobin is basically because the vector we made carries the human alpha globin gene, because it was like a gamble. We didn't know if it was going to work in mice as well as the mouse alpha globin gene. So this is a chimeric alpha globin gene because it's made of 2 mouse beta globin chain and 2 human alpha globin chain. And you can see, and I can tell you, the hemoglobin is not identical to neither mice or humans in terms of some of the properties, but the mice are alive. They basically survived, they didn't die, they didn't have this problem that I showed you before. And we can look for them, look at these animals a long time, and basically they're rescued with a stable copy number, etc. And all these animals basically are rescued with 1 copy of the vector or above. And so another piece of information here is, I mentioned before the spleen of these animals that don't have the vector with the alpha thalassemia is very large. You can see that compared to wild-type control. And then the vector, one of the mice treated with the vector shows a very normal spleen. You can see here, for instance, the quality of the red cells, in a mouse not treated with the vector, and now the vector treated mouse and very similar to a wild-type animals. And so, and also, we also treated patient cells. We have a chance to collect CD34 cells, peripheral blood of patient with alpha thalassemia. And basically, this is a schema that shows using a number of models and patient cells, we were able to decrease hemoglobin H in proportion to the amount of vector utilized per cell. And so, in conclusion, for the alpha thalassemia part, basically, we were able to generate the first adult mouse model of thalassemia that show really strong features of this disease. And then with a vector that express at least 1 copy per cell in hematopoietic stem cells, so the alpha globin gene, the human alpha globin gene, we can correct these animals and basically do secondary tertiary transplant, and then basically the phenotype is corrected for a long time. So let me switch now to X-linked sideroblastic anemia. And I just want to mention, I'm sure that everybody's aware of this disease. This is a disease where basically there is a mutation. These are hypomorphic mutation in a gene called ALAS2, which is basically what you need to know is the first gene that's responsible for making heme in erythroid cells. There are 2 genes called ALAS in our body, one called ALAS1 and called ALAS2. ALAS1 is expressed everywhere. ALAS2 is very important in erythroid cells. And so if you have mutation in ALAS2 gene, the rest of your body is totally fine because the ALAS2 basically is responsible for making heme in many cells, which is heme is important not only for hemoglobin, for a number of enzymatic reaction. But if you have mutation in ALAS2, basically you have the reduction in production of heme, and this is a problem for making hemoglobin. However, the mutations in the patient are hypomorphic generally because a knockout normally is incompatible with life. However, it's an X-linked gene. So what happens is that you have women that are carriers. And normally, they have 1 copy of the gene and they have X inactivation, which is random, and normally they do not have a problem. However, there are, over time, there is skewed inactivation of the X chromosome. And some of the patients have the worst phenotype are actually women because the second gene is mutated with maybe a very strong deletion or stop codon. And when the skewed inactivation happens such that the majority of the hematopoietic stem cell deriving can make red cells are those with the mutation, then these women basically have a very, very severe phenotype. While for men, normally it's hypomorphic. And so the phenotype may not be as severe. So and this is basically what I just said. There is this mutation, there is all this relationship between the mutation and the disease. And one thing that I didn't mention is that the patient with the X-linked sideroblastic anemia have a very peculiar feature, which is basically the presence of ring sideroblast, okay? However, people tried before to make mouse model with ring sideroblastic anemia, and first of all, the phenotype was not very strong, and second, they never saw ring sideroblast. So we decided to make a very strong model. We decided to go for let's go for a nuclear bomb, so make an inducible gene in the sense that we can basically make it knockout. So completely abolish the production of the ALAS2 gene. And again, we made a lentiviral vector. In this case, again, the usual story is software, hardware. We use the software to express the ALAS2 gene in erythroid cells using the Beta-Globin software. Because if you think about it, when you need to make the Beta-Globin gene is when you need to make a heme. So basically expressing the ALAS2 or the Beta-Globin gene or the alpha-globin gene at the same time is what you expect to be efficient to restore the production of hemoglobin in these red cells. And so I just want to show you that this mouse model is the first one that shows ring sideroblast. You can see here some of these features of this ring sideroblast. And the other thing is very interesting. In this mouse model, we observed that basically this is a flow cytometry analysis, basically allows you to characterize the erythropoiesis from normoblast to nucleated red cells going through like in poly or orthochromatic cells and reticulocytes. And basically, this is very, very nice because the block in erythropoiesis happens exactly when the cells start making hemoglobin, so the polychromatic stage. And so basically, we have a very strong phenotype, and the mice basically stop making red cells the moment you induce the deletion of the ALAS2 gene. So to make a long story short, the mice die rapidly after you basically eliminate the gene because they start making red cells. They don't really make red cells. However, if you add the lentiviral vector, you can rescue these animals, but you need to have at least 50% of the cells with the vector. Otherwise, the overwhelming majority of the erythroid cells that don't have the vector will still be impairing the ability of these red cells to rescue the mice. And if you look at those animals that have more than 50% of red cells of hematopoietic stem cells with a vector, you can see basically that now the animals with the, what I indicated with XLA plus the vector show hemoglobin levels that are almost in the range of normal mice. And they have different additional features. They have a better, normalized splenomegaly. These animals, by the way, they also suffer by iron overload, which is a characteristic associated with many diseases of ineffective erythropoiesis. This is another one of those. And you can see, for instance, in the liver, that iron is present. It's a blue color. It's called Prussian blue. It's a blue color. It's present in these animals with X-linked sideroblastic anemia that goes completely away when you basically treat them with a vector. And so, in conclusion, basically, for this second part of the talk, we've been able to make a new mouse model, X-linked sideroblastic anemia, that shows really strong features of this disease that we can really study. Now we're doing metabolomics and other characterization of mitochondrial integrity, et cetera, because we think that this is a disease where mitochondria, the death of the cells, depends on the quality of the mitochondria. But another thing I want to mention is the vector really rescue a very severe model of X-linked sideroblastic anemia, which is really not what you see in the human population. So our goal is, we do really believe that this is a system where in presence of hypomorphic mutation, a little bit of the vector will probably make a big difference for these patients. And so we're now working on trying to characterize these differences really to get to the point. But I want to finish with my last two slides, just mentioning very briefly the work that we do in addition to what we call gene addition and gene complementation, which is the really developing technology that do target hematopoietic stem cells in vivo, as I mentioned before. So why this is, I think it's important, because you can imagine if you can target hematopoietic stem cells in vivo directly, you don't need myeloablation. So all this conversation we're having now about the toxicity will be completely gone, right? We can eliminate random integration, possible integration associated with the toxicity, genotoxicity associated to reactivation of oncogene by random integration. And we can also, and we are working on that too, also elimination, maybe create a new form of myeloablation that are not as toxic as busulfan. Why we think we can do that? Because we proved that basically these lipid nanoparticles can go to the bone marrow, but they don't go to the germinal cells. And so if now we have basically a system where we deliver what we call killer RNAs or pro-apoptotic mRNAs, and we basically can kill the hematopoietic stem cells and then basically transplant the mice. But then, and we know they engraft, and when they bring them back to their cage, they can still breed. So they can have progenies, because basically germinal cells have not been touched and don't show any of the toxicity that are associated with busulfan. So we're working on that and hopefully putting things together to show that we can treat beta thalassemia using this approach. And so the future direction is basically now that we have this number of tools. I don't want to say that gene addition or ex vivo technology is going to disappear, because there are many, many things we need to do, and there are it's going to be a long road before we can do everything by the in vivo technology. But for instance, if you think about base editing, which is really the most advanced way to target the correct mutation, we don't really have yet the technology to target every single mutation. The base editors have limitations, and also the way you design the single guide RNAs, et cetera. Alpha thalassemia is associated with large deletion, so we cannot really do gene editing when the gene is missing, right? So there are a number of things where ex vivo and in vivo technology need to go together depending on the characteristic of the patients. And so one of the things that we're doing now, as I mentioned before, we're going into direction in vivo gene therapy, but also the depletion of the hematopoietic stem cell with less toxic approaches. And also we are generating a large number of humanized mouse models where basically they carry the mutation in the human sequence. So then we can test our technology to correct this mutation. When that works, hopefully we can then deliver that to the patients. CHOP has been the first center, you probably know, where the first patient was treated with in vivo gene therapy for a metabolic disease, because delivering this technology into the liver is actually visible already. So the question is to move that to the stem cell, which is a little bit more challenging. With this, I finish my talk and happy to take any question you may have. Thank you.
Thank you. It was an amazing talk. I want to get back to one of your last comments about the liver. That was also my understanding, that the liver is very easier to edit than the rest. So when you say we want to target stem cell, do you mean we're going to edit, or we're going to also target hepatocyte, but they're not going to edit there? We're going to have a strategy to specifically edit within stem cell, although we know that LNPs will get into hepatocyte.
Yeah, so there are a number of things you can do to avoid liver targeting. So number one, in our technology, we use antibodies that target a specific receptor expressed on hematopoietic stem cells. And so if you don't do that, the majority of LNP, they still target a little bit of the stem cells, but very low proportion, but they still go to the liver. Now, if you put antibodies, they go primarily to the liver, but they still go to they go to the bone marrow and the stem cells, but they still go to the liver. So another thing we did to prevent expression in the liver is to use a sequence which is recognized by a microRNA expressed only in the liver. Okay, so you make your RNA, and then you add a sequence which is recognized by microRNA, which basically induce, basically eliminates the RNA, right? And that only happens in the liver. So your RNA is going to be still active in the bone marrow, but not active in the liver. And you can use a number of strategies, bifunctional antibodies, et cetera. So there are ways to go around. Thank you for the question. If you're interested, what we're trying to do in our center, since nobody asking me the question, since we've been doing everything in-house, in terms of for the first clinical trial, beta-thalassemia with our lentiviral vector, we're lucky, I'm lucky, I work in a center where this is possible. So we're trying basically to do all the trial without sponsorship from a company. And so our goal is to hopefully show that we can treat a patient with 1/10 of the cost that what the company now asking for. And so if that's possible, then we can automatically potentially charge the insurances in the United States, different from here, I know, but providing gene therapy approach treatment for much lower cost compared to what is normally now requested for Bluebird or Vertex.
Yeah, Stefano, amazing, amazing. I don't know how people can do so much in so much at a time. But anyway, you don't have ADHD like I do. One of the things that really struck me, is it possible if you can modify the gene, can you modify the structure of the gene that you're inserting in such a way as to alter its hemoglobin, their oxygen affinity? And I know this is a different kind of an approach, but that would be really cool.
So you're talking about alpha thalassemia?
Yeah, alpha thalassemia.
Yeah. So I don't think I discover anything particularly, novel. I mean, I think what the mouse model really, in a way, okay, let me say, I think if you have a patient with alpha thalassemia, right, and you rescue this patient in utero, you know that automatically you need to transfuse this patient, right? So you don't want to wait for this patient to have severe phenotype before you start the transfusion, right? And so I don't think that it never been seen, right, how much this patient can make so many red cells in circulation. I think it's indirect data from Ali that shows if despite the transfusion, they still make a lot of red cells with hemoglobin H in circulation, right? And so our model, because in mice, you can really push the system, right? And say, okay, I make a model, I don't treat the model and see how far it goes, right? And I think the fact that there is such a profound binding of oxygen to this hemoglobin to the point that mice are extremely hypoxic. You have like such a huge increase in erythropoietin levels that you making an humongous amount of erythroid cells, even if they're completely inefficient, right? But they still go in circulation, and then they make this large number of red cells. So I don't want to say, leave a patient without transfusion, see what happened, but that would be what I would expect at this point from the model to see in a patient with alpha thalassemia, severe alpha thalassemia.
I mean, clinically, and we learned from Ali's papers how we do our stuff in Los Angeles too. But we aggressively transfuse them, and we drive their fast hemoglobin down, keep it under 10%, and we view that hemoglobin H as being toxic.
Yeah.
So so they call us when they're doing the in utero stuff. We exchange them the moment that they're born to get rid of all of this and get them on transfusions, and then they're fine. I mean, from a postnatal oxygen delivery, but they have all these other anomalies.
Right.
And as you know, alpha globin it has other problems. I mean, it regulates nitric oxide, it regulates vasoconstriction in the postcapillary vein by killing. So if you could correct them in utero, I don't know.
Oh yeah. So
it seems if you can correct correct the insert a gene that doesn't produce.
Yeah, so one of the projects we are developing, I mentioned before, with the deletion is obviously very challenging, but one of the things we know for a fact is that LNP can be delivered in utero. So this lipid nanotechnology is actually pretty good. So right now we're making a mouse model of constant spring, okay, which is a mutation in alpha thalassemia. It's basically, the stop codon is not a stop codon anymore, so it makes an extra longer chain, and that's pretty bad. And so we're going to try to inject the moms with this LNP that have, and the embryos that have the constant spring, and see if we can rescue that.
So give them a different hemoglobin that has some ability to release.
So hopefully the goal is to make at least 50% of this constant spring normal, and so then eventually they will be able to survive with, hopefully, carrier trait or something like that.
That would be. I mean, I actually think you look at the statistics with this, there's got to be a lot more patients out there with this than we think. They have, the babies die and nobody ever knows. So that's a big problem.
I think sickle cell opened the gate to discuss about these therapies and to discuss about the treatment of the patient, but I think we need to open the umbrella to other hemoglobinopathies like SC, alpha thalassemia, and also all the rare red cell disorder, because no company is going to take care of X-linked sideroblastic anemia patients. So 50 patients, so they don't make money.
Thank you so much. It was a wonderful presentation. I learned a lot, and it's amazing how you bring this model from the mouse and then to the clinic. really fast, actually, so that's amazing. And my question was about what is the current state of in utero gene therapy and what's happening right now? Are there any trials going on? And I mean, from an ethics perspective, probably it's easier than other diseases just because these babies would die unless they have access to intense in utero transfusions. But even when they're born, they can have neurological sequelae and they have other damage. So are you aware of what's going on, if there's any trials
So for alpha thalassemia, I think there's been a trial in California, but with transfusion of donor mother stem cells, with the idea that once the patient was born, it could be easily transplanted with the same source of cells, but it didn't really work out, from my understanding. In terms of like doing gene editing in utero, there's nothing in terms of trials. I think we need a little bit more data. I mean, we work a lot on mice, but in collaboration, we're now doing sheep and non-human primates. I think we need to go through that route before we can really think about it. Thank you.